let's look at a systematic way for determining if a linear transformation is one-to-one and if it's onto. So these two theorems are going to tell us this. If T is our linear transformation, it's one-to-one if and only if the kernel of T is just the zero vector. So remember what that means. If you have T of x is matrix A times x, it means if you solve out AX equals 0, if the kernel is 0, that means that you have no free variables. It also means that if you take the reduced row echelon form of A, it's going to have a leading 1 in every column. So a leading 1 in every column. And that's going to be probably the best way to check for this. All right, what about being onto? This says if T maps V to W be a linear transformation where W is finite dimensional, all of the cases we're going to deal with will be finite dimensional. So it says T is onto if and only if the rank of T is equal to the dimension of W. So again, I'm going to say let's let T be T of x is A times x. So it says the rank of T equal to the dimension of W. So the rank of T is the number of leading ones. It has to be equal to the dimension of the codomain. And so those are the two things that we're going to look for here. If you think about what this means, the rank of T, that's the dimension of the range. And it's basically saying, does the range have the same dimension as the codomain? So let's look at some examples here. I want to go through these examples, and as far as like just getting the answer, really all we're going to be doing is looking at the number of leading ones in the reduced row echelon form and checking these things. But I'm going to give some explanation with them too, because comparing it to these definitions or theorems, I mean, it's good for getting the answer, but it's not good for understanding. So let's look at this. A is this matrix here. If you think about what this does, this maps R2 to R2. That's because if you were to multiply this by a vector and then get another vector, this would have to be a 2 by 1, and that would have to be a 2 by 1. But if you take the reduced row echelon form, let's see, this is going to be 1 3/2 0 0. If you look at that, there's only one leading one. So we don't have a leading one in every column. So it's not one-to-one. And then the other question is, we only have one leading one, but we need two of them. So it's not onto. Now the reason is, if you look at this thing and think about what it does, there's only one leading one here, so that means that the range, also the column space, same thing, has dimension 1. So what does that mean? It means that this linear transformation with this matrix, it maps R2. It actually just maps it to a line in R2. How do I know a line? Because the dimension over here is only 1. So it doesn't map it to the entire thing, and therefore it's not onto. Okay, this next one, if you row reduce this, I mean, this one also maps R2 to R2. And if you row reduce this guy, you get the identity. So you've got two leading ones, and you've got a leading one in every column. The leading one in every column tells you that it's 1 to 1. The fact that you have two leading ones means that the range is a plane. Maybe I should say the range is two-dimensional, 2D, also known as a plane. And it's a plane within R2, and the only plane in R2 is just the plane itself. So therefore, it is onto. All right, let's look at this next one. This one, let's see, if we were looking at this, it would map R5 to R3. Because you can multiply this by something with 5 guys in it, and then you get 3 there. So let's look at its reduced row echelon form. All right, I'm going to get Octave to do this one for me. I have this in here as A6. So if I row reduce that, I get this, and then I get -1/3, 4/3, 5/12, -5/12, 17/12, -5/12. And truthfully, all those numbers over there, as far as just for answering this question, they're not that important. The important thing here is we don't have a leading one in every column, so it's not 1 to 1. But we do have 3 leading ones. So that means the range is a 3D space, 3D subspace of R3. Well, the only three-dimensional subspace in R3 is all R3 itself. So therefore, it is onto. Before we go to the next one, let's talk about it. It's not 1 to 1. Well, what's happening here is it maps stuff from R5 to R3. So if you think about it, that really can't be 1 to 1 because you're taking everything from a 5-dimensional space and cramming it down into a 3-dimensional space. There's no way you can do that without some of the stuff running into each other. That might be hard to visualize, but you can also think of, like, if you took everything in a 2-dimensional space and crammed it down into a line, some of those points are going to wind up getting squished together. So it can't be 1 to 1. In general, anytime you're mapping from a higher dimensional space to a lower dimensional, it can't be 1 to 1. Okay, let's look at this one. We've got A is this matrix. So we could put 4 things. When you multiply it out, it would give you 3. So this is going to map R4 to R3. So really, by what I just said, it can't be 1 to 1 because we're going from a higher dimension into a lower one. If you think about why that's true, let's see, A7. Another way to think of it is there's no way you can get a leading one in every column. There's no way you could have a leading one in every column here because you can't have more than one in a row. And there aren't enough rows here to... there are more columns than rows, so you can't have a leading one in every column. Our leading ones here are here and here. So this is not one-to-one. And what about onto? Well, we've only got 2 leading ones, and we needed 3 in order to get to there. So it's not onto. And for a bigger explanation of why it's not onto, this thing T maps R4 to a 2D space, 2D subspace, a plane in R3. So it doesn't map it to the entire thing, it just maps it to a plane. So it's not onto. All right, last example. This one maps, let's see, we'd have to have 3 things here. Whoops. And we'd have 5 here. So this maps R3 to R5. Okay, if you think about this one for a moment, there's no way this could be onto, because if we're mapping something from 3-dimensional space into a 5-dimensional space, in a sense there are more points in R5 than there are in R3, so there's no way we can hit everything. If you take the reduced row echelon form of this, what do we get? Okay, we get an identity matrix on top with a row of zeros underneath. And I totally miscounted. That's not R3 to R5. It's R3 to R4. So we get this. We have a leading one in every column, so it's 1-to-1. And let's see, we have 3 leading ones, but we're in R4, so it's not onto. And it's not onto because this maps R3 to a 3D subspace of R4. All right, that's it.